Hello and welcome back to 5G Hack Them All 2022 for a second week of our summer course. And week 1 was amazing. We have totally 10 lectures, and I would like to notice that all of the lectures are mandatory to refer your learning diary. And I would like to also say that great work.
Pitäis muutella.
Hello and welcome back. Can you hear now us? Okay, sorry, we have some technical difficulties. That's normal nowadays. Yeah, welcome back to 5G Hack Them All 2022 for second week of our summer course. I would like to say that first week was amazing. We have 10 lectures, and I would like to say that all of the lectures are mandatory to refer your learning diary when you write that, or I hope most of you already written your diaries from last week. And about the project work, great work so far, and we will send you feedback about your pitches on Friday, latest tomorrow.
So now the second week starts. We'll have totally 6 lectures, and because there's only 6 lectures, there's plenty of time to work with the project. And there were some difficulties contacting your teammates. So if you know that you're attending project work but you haven't contacted your groups yet, do it ASAP. And about the final quiz, the questions about mandatory lectures and general about 5G, and the final quiz will be open until Thursday 23rd, and it will open on Wednesday evening. So all the lectures are recorded, and there can be found on YouTube. There's a link on my courses, so you might want to watch those before you do the final quiz. And then also this week there will be some optional program in the evenings. It will be on the same Zoom link, and there will be some talks about 5G and XR and VR and so on.
And something about the final pitch. So this will happen on Friday afternoon, and it will be totally 7 minutes long pitch, and then we have like 5 minutes for questions and answers from the challenge owners and other course members. And all the challenge members will be online on Friday, so you'll get instant feedback. And after the final pitches, please download your slides on my course, so we will send all the slides to challenge owners, and they might contact you afterwards also. And we will publish this pitching schedule during this week.
Yeah, so now we will hear this week's first lecture from Yu Xia, and she will be talking about extended reality. So the lecture will start at 1 p.m, so there's 10 minutes time before the lecture. So thank you, and we'll see you then.
Thank you.
Like kysymistä.
Good afternoon, everyone. Welcome to today's lecture on 5G for XR. My name is Yu Xiao. I'm Associate Professor from Aalto University School of Electrical Engineering. And I'm leading the Aalto Wearable System Lab, and this is a multidisciplinary group. And we try to solve real-life problems with human-centered design approach, as well as advanced AI, XR, and sensor technologies. So today, we are going to talk about XR. I will start with an introduction to the enabling technologies of XR, and then continued with the technical challenges from networking perspective, and see what 5G can offer for XR. Okay, so now let's start from what is XR. So what is XR? So I think many of you have heard about some terms like virtual reality, augmented reality, or more recently, mixed reality. And I often hear this kind of comment say, hey, is XR actually the emerging immersive technology? Meaning, is this like the fourth category of immersive technologies? But actually not. So XR stands for extended reality, and it is an umbrella term for all the immersive technologies. So meaning that an XR actually consists of the three categories, VR, AR, and MR. And among all the three, virtual reality is the only one that is like that provides a completely digital environment. So what it means is that what you see is just a virtual environment. You don't see the physical environment at the same time. And then the augmented reality is different. So augmented reality, you can consider it as an overlay of digital content on top of the physical environment. So basically you see the real world, kind of like a camera view of your phone. And then you see some digital content on top of that. For example, now you stand in front of a building. So maybe the street address of this building can be shown on top of this building. So that's augmented reality. And nowadays you don't need any special devices in order to use the AR. You can use your smartphone. And the third one is mixed reality. So this is basically a combination of VR and AR features. And this is like a relatively new technologies if you compare it with VR and XR. VR and AR. Okay, so now we will go into the details to see what are the enabling technologies and what kind of hardwares are available. So we will start with VR. So in order to use VR applications, you will need a VR headset. And there are many different models of VR headsets, starting from low-end ones like Samsung Gear to the high-end products such as Vibro Eye, Oculus Quest 2, or Vardio XR3. And some of these headsets are PC powered, which means that you will need to connect your headset with a computer through cables. And the others are wireless ones, meaning you don't necessarily need to connect your headset through cable to a computer. So you can just use it like wirelessly. And then if you have a VR headset, what can you see then from the headset? So in practice, there has been these two main categories. So the first one is this panoramic video. So imagine that during the COVID, you might not be able to visit an apartment when you try to buy or rent one. And on many web portals, you can already find this kind of panoramic video. So that has been captured by, for example, the owner of the apartment or real estate agent. So they might be using a 360 camera to capture this natural scene or this real world scene. And then when you put on your VR headset and you load this video there, you would be able to browse this apartment from different angles, from different locations. And the same thing happened to some sports games that the fans of football game, for example, you would be able to put on the 360, you will be able to put on your VR headset and then try to watch this game. You can choose, okay, so now there is a goal I would like to see from different angles, and that would be possible with this VR. And the second category is this computer-generated environment and content. So you could imagine that those, for example, those figures, the things, they are generated using some computer programs, some predefined models, for example. And this kind of computer-generated environments has been widely used for computer games and as well as some training scenario. So for example, for surgical training, right, you don't always have the real human bodies or things like that to train, but with this VR, it would become much more convenient to train those doctors. So these are like two type of, let's say, content, I would say, or environment. And then if we come back to this hardware, to the VR headset, so if you simply open a specification of one VR headset, you would easily find some parameters like field of view or angular resolutions like that. So what does this mean? So first of all, field of view, FOV, this is a very important metric. So you can imagine that in the virtual environment, the vision of the users, it evolves in the sphere, so which would unfold 360 degree horizontally and 180 degree vertically. So in practice, you put on the VR headset, you can move your head or turn your head, then you would be able to view the 360 degree video there. But then why you need to turn your head is because if you just stay in one position, you can only view a part of this spherical data, only a part of that. And that is called the field of view. So for example, I might be able to see only 19 degree or 100 degree if I don't move my head. So then when I move my head around, I would be able to load another thing, which is another maybe 19 degree. And the modern consumer grade this VR headset, it typically have this field of view within 19 degrees. But of course, recently there have been some new headsets such as this Valeo VR3. It provides a 115 degree field of view, but still this 115 degree is still not as wide as this humans natural field of view. So what does it mean? So it means that humans, and so we are humans, we are able to see about 200 degree horizontally of the field of view naturally. But when we put on the VR headset, we cannot see 220 degrees. So we can only see maybe 90, maximum 115 degrees now. So that is like one limitation. And then another parameter you might find from the specification is called angular resolution. So what does it mean? So we talk about field of view. So we talk about how many degrees. So it's kind of the angle, how many degrees. So this angular resolution actually measures the number of pixels per degree. So you can imagine, it's just like, for example, our TV or computer monitor. And we are usually say, for this one display, what is the resolution? It might be, for example, 720p 1080p or 4K. So that's like the resolution. So it's like a number of pixels we are talking about. And then when it comes to the VR headset, it is the same thing, like it is also a display, right? So then if the number of pixels, the total number of pixels is fixed. So when the field of view increases, then we will have to lower the angular resolution, meaning for each degree of this field of view, then the number of pixels would reduce. So there is a trade-off there. And there are also the third one mentioned often in the specification is called refresh rate. So for example, for our computer monitor, a typical refresh rate is 60 Hertz. So what it means that the display is able to draw a new image a maximum 16 times per second. The 16 Hertz means how many times per second the display is able to draw a new image. And for the VR headset, we would expect also quite high refresh rate. Why? It's because when you reflect these on-screen images, right, and then this is expected to be as high as how fast the brain can process it. So let's put it in this way, that if you are not able to reflect these on-screen images fast enough, it might be slower than what the brain can process. Then that would cause the VR sickness. So you might feel sick after using it for example, you might already feel sick after using it for 15 minutes. So regarding the refresh rate, we would expect 19 Hertz and beyond. And for the resolution, we talked about the resolution earlier. So we would expect at least 2K by 2K pixels per eye, or ideally even higher with 8K by 4K per eye. So you can imagine that we have two eyes, right? So then per eye, we expect something like this. So definitely the resolution of the headset in the market today, they cannot really achieve that level yet. So, but that's at least like the ultimate goal. I would say we would expect this high resolution display. Okay, so we have been talking about those visual quality, and it is very important from the user experience perspective. We want very high resolution, we want high wide field of view, we want high refresh rate. But this is only part of the user experience. So we also would like to have high resolution audio, and we also expect often ultra low latency interaction with these VR devices or with the VR applications. So imagine that people have been, for example, using some playing tennis, for example, in the virtual environment, right? And then it means that we will need the hardware and software that will be able to track our body movement, and then the VR application would need to respond immediately to this user input. So this required both very accurate tracking plus very low latency processing. And if the data is not processed locally, then we will need low latency data transmission as well. So we will come back to this later, because this part is also closely related to the 5G for XR. Okay, so we will first talk a bit more about the motion tracking, just to give you an idea, what kind of motion tracking technologies have been in use nowadays. So, so the first one is this kind of infrastructure setup. You might have seen it in your real life, that if you have been using, for example, Vive Pro Eye, like this kind of headset. And in one room, you might need to set up 2 base stations or even more, depending on the size of the room. And this kind of base stations, you can imagine that it is like some laser emitter there. And then you would have this controller in hands, like in this figure, it has this controller. So then when you have all this setup, then this system or this so-called Sting VR tracking in this figure, it would be able to track the movement of your body, including the, for example, the orientation, the velocity, the angular velocity. So this is something that has been used for a while, and it provides actually quite precise tracking nowadays. And then there are also, but this one is like you need to have it, you hold this controller, so it's basically tracking the location of the controller and your headset. But if you want to have this full body tracking, meaning that I would like this VR to be able to really track, you know, where my hands, my different joints, then one way is to put this like this HTC Vive tracker, this kind of sensors. So you can place these sensors on your hands, on your shoulder, your elbow, you know, those joints. So then also you need this base station, and this would be able to track then the locations of those joints and to estimate the full body postures. And more recently, there have been also other technologies, for example, smart garment, like this Captograph or Bebop sensor, so different kind of smart glove that has been proposed for hand tracking, or some devices like this kind of leap motion. So they have been used for tracking the hand movement. So for example, in Oculus Quest 2, they have integrated this hand tracking into this headset. So if you put on the headset, then it would be able to actually detect the hand gesture. So you'll be able to implement some gesture interaction into your VR applications. And besides motion tracking, the eye tracking is also getting popular. So for example, HTC Vive Pro Eye, so it has integrated the eye tracking into this VR headset. So with this eye tracking, what it means that it would be able to kind of detect where this user is staring at. So for example, on this figure, you can see that if somebody goes shopping with this kind of eye tracking glasses, then the system would be able to recognize, hey, this person is actually interested in this product or in this type of products. So it can be quite useful for example, for marketing. And by the way, here you see these eye tracking glasses. And as I said, that they have, of course, the standalone eye tracking glasses, and some of these solutions have been integrated into the VR, and also some have been integrated into the mixed reality or AR glasses as well. So these are like the tracking technologies. And so far, all these eye tracking or motion tracking, or especially eye tracking, actually, it has been kind of computational intensive. So these kind of glasses, it need to be connected to a computer. So it cannot actually process all the data locally, because it required quite a lot of computing power. Okay, so that's about the VR. So we have some idea about what kind of hardware devices are available for VR. And then when it comes to AR, as I said earlier, that you can simply use your smartphone or some tablet that supports, for example, AR Core, AR Kit. So you can then run the AR. So I think one of the most famous AR game is this big, Pokemon. Many people have probably played Pokemon on your phones. And then there are also some AR glasses in the market, but I must say that they have not really been widely used because of a different type of technical limitations. So for example, it also requires to be connected to computers to process the data, or maybe because the field of view is not wide enough, and so on. So many different technical limitations. And the third category is mixed reality. So as I said earlier, that it is a combination of VR and AR features. And earlier we have like a Microsoft HoloLens. And in Finland, we have this Mario XR3. So these are quite advanced MR devices. But compared with AR, of course, one challenge is that those devices, they are relatively heavy. I mean, MR glasses, they are quite heavy to wear, and it is difficult to use it, for example, in the factories, right? Because you might need to wear the helmet, and then if you need to wear this kind of MR devices at the same time, it is not so easy and comfortable. So I think technology-wise, this has developed very fast, and of course, there's still a lot of room to improve them. So now we have kind of given an overview of these devices. Now let's look at this like interaction scenario. So let's go deeper into the technical requirements. So to be more precise, we will look into the technical requirements from networking perspective. So we will pay attention to the metric called end-to-end latency. So first of all, what does end-to-end latency mean? So if we take the 360 video as example, so the end-to-end latency means the time it takes from content collection, for example, you capture the video, to the rendering to the terminal display, like when the end user really see it from their VR headset. So this is the end-to-end latency. And from the interaction perspective, we can divide VR scenarios into 4 categories, starting from weak interaction and to strong interaction and to ultra strong interaction. So regarding the weak interaction, so a live broadcast of sports events is one like typical example. So you can imagine that if you put on the VR headset and try to watch a football game, so the content is streamed from a remote server to your headset. It is quite similar than watching YouTube from your computer. And for this type of scenario, we can tolerate a relatively high latency, so something like 10 to 20 seconds. But when we expect, let's say, more interaction with the VR application, for example, if we try to play the game, then this VR application server would need input from the user. For example, we can control the playback of some video content, or based on our motions or other kind of actions, then the content to be rendered would be different. So in those cases, then we would expect much lower latency. So take this VR sports game like a ball throwing as example. So we would expect something less than 20 milliseconds. So now we are going to give a couple of concrete examples to show how this kind of VR scenarios or VR applications has been implemented and deployed, and what are still the technical challenges. So from latency perspective, what has been the bottlenecks So we will start with the first one, which is 360 video. And actually in April 2020, in US, so this telecom operator Verizon, together with a couple of other companies, they made the first 5G AKVR football live stream test. So you can imagine that they kind of deliver these live streams of these football games to some users sitting like 200 miles away. And in practice, they deployed to this type of Intra 360 Pro 2 AK camera. You can see from the left side of these slides. So they deployed two this type of live streaming cameras on site. So basically they have put one as a goalpost cam and the other one was mounted on the sky cam, like this one in the middle. And this kind of video captured in real time was then sent to a local server. So we can see maybe from the next one. So because you have this video captured by different cameras, and these streams needs to be stitched. So you can imagine that the images need to be stitched in real time on some local servers. And after that, they are delivered through the internet to the remote users. And obviously, this kind of video processing here, I mean, stitching those AK HDR VR stream in 13 frames per second has been quite heavy. So this actually takes some time here. And if we take a look at this figure, it gives kind of an overview of the whole system. So as you see from the previous slides, you have the camera, you have some local processing, and you create this kind of AK stream. And after that, they actually deliver it, convert it, and deliver it through some TV system. And then through the fiber network, the data was sent to Miami, to another city, 200 miles away. And after that, they were using this 5G network. You can imagine as a last hop to stream this VR stream to a dome. Actually, they made a test that they have many users sitting in one dome, and then when they receive these streams, they decode the streams, and then they project this to this dome. You might see part of that using 6 projectors. So this is how it works. And they did the measurement that the end-to-end latency in this case was 3 seconds. It is actually pretty low already. If you are using the 4G network here, it would definitely take more than 3 seconds in this case. But you can see that was the test done in 2020, and the 3 seconds is kind of the results they got at that moment. Okay, now let's take a look at another example. As we said that, you know, there are 2 types of this kind of VR. One is this, like the 360 video, and then the other is this computer generated environment. And for this type, the second category, there is a very important step, which is called rendering, because we know that all those like 3D graphics or animations, they need to be kind of rendered. So so they have this software component called the rendering engine, and it generates this animated 3D graphics. And the rendering is actually a very kind of computationally heavy, expensive part. And usually you need really good this graphical cards, of course. And still, if you want to calculate and display it in real time, it is not that easy. So we expect usually this rendering to be done with a frame rate between 20 to 120. But as I said, that it requires actually quite a powerful machine if you want to render this high resolution VR streams and with a high frame rate. So this is still like kind of like one bottleneck, I would say. And then there has been a couple of proposals on how to solve this problem. The one is called foveated rendering, and the other is cloud-based VR. So traditionally, we want to render all these graphics locally, meaning like on these end user devices, like on the XR devices. But then you know that if you have very high resolution and very high frame rate, that is like a lot of workload. And then when people try to propose this foveated rendering, because we notice that for the human eyes, so the human eyes work in the way that the eye is only high resolution in the very center. So meaning that if you look around the room, then only what you are directly looking at is in high detail. Everything around that area isn't as critical clear. So in fact, that foveal area is just 3 degrees wide. So if our eye works like that, then does it make any sense to actually render everything with high resolution in all areas? The answer is no, it doesn't make sense to work like that. So a better solution is to render where you are directly looking in high resolution and then render the other parts with a significantly lower resolution. And that is the basic idea of foveated rendering. And of course, you might have noticed that then this requires this eye tracking to be very accurate. So you need to really be able to accurately and precisely tell where your eyes, the user's eyes, are looking at. So this is like the requirement. So you need to have the accurate eye tracking, but then it becomes a little bit problematic here that because eye tracking itself is also computationally expensive. Yeah, and it might not be 100% accurate. So there is still challenge to be solved if we go for this foveated rendering. And then the other solution is called a cloud-based VR. So we know that if our VR or XR device, they are not powerful enough, but there is like some cloud, for example, Amazon or Google or Microsoft data center. So they have a lot of computing power. So the question is then, can we utilize those computing power? Can we offload this compute intensive task like graphic rendering to the remote data center, to the cloud? And the answer is yes, and actually that has been implemented in many systems. So then this kind of cloud-based VR system will be implemented in the way that this end user device will serve mainly as an input device and a display. So as an input device, meaning that it would, for example, detect some people's posture or location or some command that was sent through some controllers, and this would be sent to the remote server, which is typically deployed in the cloud, I mean, to this kind of game server. And then on the game server, they will calculate the game logic, will render the graphics, and then they will basically encode this into video. So meaning that those rendered game scenes will be delivered back to the client as a sequence of encoded video. So you can see from the figure here. So the rendering, after rendering, the rendered game scenes will be encoded and then delivered to the end users. And then this, at this end user device, the received video will be decoded and displayed. So starting from the input collection to the display of this content, and this is like the end-to-end latency. And for this scenario, they have also another term called the motion to photon latency. Yeah, it's also called motion to photon latency. And for many interactive games that we would expect this kind of latency to be less than 20 milliseconds. But in practice, it is not easy, because if you just simply think the network latency from your mobile device to a remote cloud, the latency is often over 100 milliseconds, and it could also varies over time. So it's not that stable. So it sometimes might be lower, sometimes might be higher. So that is definitely one challenge. I mean, from the networking latency perspective, this part of latency could be long and may not be stable. So there is then one way to solve that problem. I mean, to kind of solve this kind of long and uncertain network latency issue. So people propose a solution called asynchronous terminal cloud rendering. So the fundamental idea of this is to enable this parallel execution of cloud rendering and streaming and the terminal reflection for display. So what it means is that, okay, so now when the VR terminal, for example, it gets the nth frame from the cloud, and then they are kind of like displaying that. But meanwhile, the cloud rendering platform is already processing the n+1 frame at the same time. So it means that it doesn't need to wait until, for the, let's say for this VR terminal to tell that, okay, now start rendering the next frame. So when the VR terminal is kind of projecting the end frame, the cloud rendering platform is already rendering the next frame. So that's the idea. So in this way, they can try to kind of reduce the impact of this network transmission latency. But then, of course, then this end-to-end latency or motion to fountain latency would very much depends on the terminal. But at least with this approach, it is more possible, or it is like easier to achieve this latency, like to achieve lower than 20 milliseconds latency. And then we have been talking about the VR, but then how about like AR or MR? So is there any kind of like architecture or framework that will work for all these XR technologies? So here we give one example to give you some idea how this kind of XR multimedia streaming can be implemented in practice. And this is something proposed by 3GPP. So you can see that in the middle is the UE, like for example, your XR device, that's like the UE. And then on the left side is the content server. So, so this category, it covers both live and on-demand streaming of the XR multimedia streams. And you can imagine that those content, they have been stored maybe somewhere remotely, and they would be streamed to the XR device. So this kind of content, it can be VR, it can be AR or MR content. So typically it might be, for example, some 3D model, some animation, some video, and anything like that. And of course, the UE would be able to control the playback, and depends on the user interfaces available. You might be able to control it just using your, like the game controller, or you might be able to control it with your motion, or even with some biometric measurement. Yeah. And in this figure, they try to render the medias on the XR, but as we mentioned earlier, that you can also choose to render those like remotely somewhere in the cloud, and then just stream the video sequence there. I mean, the sequence of the encoded video there. And then there is one interesting kind of component here called the spatial computing server. So what is that for? So imagine that you are playing, for example, an AR game, a multi-user AR game, and you would like to know, for example, you have a couple of people physically located in the shopping mall, and you are playing a treasure hunting game. And then actually this application server, it would need to know like the surrounding of each players or even locations and things like that. So how would that be implemented? So from each XR device or from each end users, they will be sending some data, for example, some visual data or initial sensor data to this special computing server. And this special computing server would then calculate this kind of configuration of the surroundings or the spatial configuration of the surroundings there. Yeah, and this spatial computing server is typically used for this kind of multi-user scenarios. And then in this figure, you can see they also draw a cloud there, and there they put the XR media storage or social media. So this is just to show that, you could also feed those social media data to this XR devices. For example, if you stand in front of a shop or the restaurants, if there might be this kind of AR application that actually show the review of this shop, on top of this restaurant or shop. So they could have this kind of applications. And this is like the social media, of course, they are deployed in the cloud. And in this figure, you can see that there is a way for you to feed this also into the XR. And there are also other technologies that will be helpful for reducing this kind of end-to-end latency. For example, try to reduce the latency of encoding, decoding, or there is this kind of 5G network slicing. So 5G network slicing is this kind of network architecture that enables the multiplexing of virtualized and independent logical networks on the same physical network infrastructure. So they have also like different technologies that could be used. And we are not going into the detail of that. But I hope you would learn that from the other lectures in this summer school. And then now let's take a look at the summary of this. So the characteristic of the VR stream, because we have been talking quite a lot about the streaming here. So quite similar with this kind of traditional video streaming. So depending on the video resolution, right, the frame rate, and obviously different bit rate or the bandwidth would be needed. And this table, just to give an example that, nowadays with the entry level VR, we are already expecting like at least 100 megabit per second access bandwidth. But that is only for really entry level VR. And if you expect something more advanced, like a 4K resolution or 60 frames per second, then we would expect 1 gigabit per second bandwidth. And note that this is like a per user. So if you have many users using the services at the same time, the same network, I mean, if they are connected to the same access point, for example, then you would need more bandwidth. And then with the ultimate level VR, that's like the ideal case. Then with the 8K resolution, 120 frames per second, then we would expect something between 2 and 5 gigabit per second. So obviously 4G would not be good enough to satisfy these requirements. We need 5G or even 5G or even 6G. So from the 5G perspective, what they can offer here is definitely this enhanced mobile broadband, the higher bandwidth, and ultra reliable low latency communication. So from the data transmission perspective, this is what the 5G can offer. But we have been also talking about this rendering, this issue that the rendering is computer intensive. Then how to also kind of reduce this processing latency, we could offload it to the cloud, but then cloud is too far away, meaning the latency, the network latency then would become too long. So the, one solution is to offload like a rendering or this type of compute intensive task to an edge cloud. So this is the ideas of edge computing. So what does it mean? It means that if you imagine, for example, a Google data center, which is located maybe in other city or even other country. So they are far away, that's like the cloud. And then we want something closer to the user. So basically you would deploy some powerful servers closer to the end user devices. So they could be, for example, co-located with our cellular base station, our Wi-Fi access point, or, okay, if we don't have this kind of powerful server for every access point, we might do so that, for example, we have this kind of edge cloud or powerful whatever edge computing node for each district. For example, we have the Otaniemi campus, we could deploy this edge cloud in Otaniemi campus. So then when students here are trying to use this XR services, so the rendering can be done just locally here. So in this way, we will be able to utilize the remote servers to handle the compute-intensive tasks while reducing the network latency. Yeah. So this is the idea of edge computing. So in summary, if you think about the XR application, they need more processing power, higher bandwidth, and ultra-low latency. And what the 5G can offer is this edge computing to solve these processing power issues and also to reduce the network latency. And then the 5G can offer a wider bandwidth and lower latency compared with 4G. So these are about the 5G. And now the question is that, is 5G then good enough? Are there still something that cannot be done with 5G? Or we need, more advanced networking technology. So there is this one thing that comes to my mind, at least one example. I think we would need something even more advanced, and that is about the touch sensation or haptic feedback. So let me just first briefly give you an introduction to this. So we know that when we are using VR, for example, currently, we use the controller or this kind of VR system. It can track our motion, can track even our emotion. But the thing is that, for example, if I'm in the VR game, right, I would like to touch something. So now you just move your controller. It's like you can see that maybe your virtual hand is touching an object, a virtual object, but your hand does not really feel it. So you don't get this kind of feeling or this touch sensations. So then we know that if we want to have a more, a better experience, we would expect some kind of hardware or in general technical solutions that will be able to simulate this sense of touch or to provide this kind of haptic feedback. And usually the sense of touch, it compasses a broad range of different sensations spread across the entire body, including like textile, vibrotextile, force, and thermal. So different kind of sensory channels. And then the tactile feedback is mainly about reproducing the patterns of pressure on the surface of your skin. So what it means that if you have this kind of tactile feedback, it's able to produce different pattern of pressure, then it would kind of help you to sense like the shape of the virtual object, the size, the weight, and even the texture. So for example, if you are touching for example, a piece of a woolen sweater, or if you are simply touching a rock, then nowadays with the VR, you don't actually feel the difference. But with such a textile feedback system, you will be able to sense and to perceive these different textures. And I would say that this kind of textile feedback, or in general, the haptic feedback devices or haptic devices, so it's like an emerging field, and there are already some devices available in the market, but it's still in the pretty early phase. So just give you some example how this kind of devices look like. So for example, they have this Sense Glove Nova. This is kind of a smart glove. It provides the force feedback and some vibrotextile feedback as well. And actually it also integrates some motion tracking solutions, and it's fully wireless. So this is one example. And from the Meta Reality Labs, they earlier published this, some photos of some microfluidic haptic feedback system they have been producing. So with this kind of, I would say, glove, so it would be able to simulate the sense of like texture, pressure, and vibration. But you might also notice that, like, look, this glove, it need to be connected. Actually, they have a lot of this kind of cables, and they need to be connected to computers. So it is not a wireless one. And another example is this HaptX glove DK2. So this also provides the force feedback and some textile feedback here. And this need to be connected also to this quite, let's say, powerful machine like computer here for processing this one. So this is not wireless yet. Okay, so how would we use this in the XR or mainly in VR? So just imagine that if you try to shake a hand or to hug someone who is physically remote, right? And then if you want to shake the hand, let's say, when you make your hand movement and the other also make the hand movement, then you should be able to feel or to sense this kind of touch, right? And you can imagine that then from the motion to actually this sensation, this feedback or this latency should be very short. It should be less than 10 milliseconds, right? And that is not the challenging part. You can imagine that when you capture this motion, right? And then you need to somehow calculate that to send this information remotely to the remote party, and then to generate this kind of feedback. So each step takes time. But altogether, we expect something like a couple millisecond latency. So this is challenging from both computing and networking perspective. But there are like a lot of potential application there. I mean, not only human to human, this kind of interaction, but also human to machine. For example, you might be controlling some machines remotely. So there are many applications. So this is kind of an emerging field, but from the networking perspective, this is also a very challenging use case. So the question for you to think about after lecture is that would the end-to-end latency between the agents in this case be short enough, and is 5G good enough, or do we need more advanced ones like 6G to solve this problem? Okay, so now we come to the end of the lecture, and thank you for attending the lecture. So if you have any questions, feel free to send to our assistants, and I will try to answer your questions afterwards.
Thank you. Next up is Eero Tiainen talking about creative industries of 5G. So Eero, whenever you're ready.